Okay, so I'm on. Good. Okay, so I'm Lyman Page, and again, like as Chuck, I just wanted to say again, it's a great pleasure to be here, and of course, it's a tremendous honor to be the recipient with my good friends and colleagues of the Shaw Prize. And what I want to tell you about, so Chuck has given you the background. What I want to tell you about is actually how we go and make a measurement and how you think about it. And it's fairly simple. It takes a lot of work to do it right, but it's fairly simple conceptually to see what we do. So how do we measure the microwave background? And in some sense, you have all seen it or detected it. And so the microwave background, so microwave, right, is it means it's in the microwave regime of the sky. It's about 1,000 times cooler than the sun, this radiation that we look at, right? The sun is about 6,000 degrees, and this radiation, right, you saw that number that Chuck showed, 2.725, right? So it's about 2,000 times colder, but you know, it's okay, well, 1,000, 2,000, we're not going to worry about that. And so in some sense, you've all detected it. Because if you've ever looked at a TV station with an antenna hooked to the sky, right, and tuned it into an inactive channel, then you get a fuzz, right? No cable, right? You have to have it pointing to the sky. You get a fuzz. And most of that fuzz comes from emission from the surroundings, which is about 300 degrees Kelvin. Right? The microwave background is about 3 degrees Kelvin. And so we say it's about 1% of the fuzz there. Okay? So what we do for WMAP is we really, we're just like very fancy TV builders. Okay? And what we do is, and you'll see it when you see it, just think of TV satellite dishes on the top of buildings. What we would do, and you could do this measurement, is with an antenna almost like that, is just take it and point it around the sky and look at the change in the amount of fuzz on your TV. Okay? Just as you point that TV antenna around the sky. And that, in essence, is what we do, but with really fancy receivers. Okay, so actually, and it turns out, so I guess TVB is over air, right? So you could do this. So channel 770, just to put it in perspective, channel 70 is about down here. Okay, and these wavelengths, so they're sort of centimeter, millimeter wavelengths. Your microwave ovens operate right here. Okay, so this is a slightly different picture than what Chuck showed of the spectrum. Let me, whoops, oh yeah. Uh-oh. Well, here, I have a laser pointer. I think it's going to come back in. There we go. Sorry about that. Okay, I have the laser pointer. So what Chuck showed you is he showed you that curve at 2.725 Kelvin. Here it is again. And I've just plotted it in different units here than he did, so it looks a little differently. And if we look up at the sky, this is the uniform emission that Penzias and Wilson saw. And not quite uniform, right? Because that's the thing we're trying to look for changes in. There it is with various measurements. This is the measurement from PHI-RAS, which was on the Kobe satellite. But if you look up at the sky, there's a bunch of other stuff there too, right? There's from our galaxy, there's synchrotron emission. It's called free emission. This is from electrons zipping around in magnetic fields. This is from electrons going by protons. And there's dust emission. We were talking about this at lunch, right? There's a bunch of dust up in the sky, and it's glowing away there. And what we do, right, is we want to make sure, since we're looking for changes as we look around in space of that curve, right? And we're looking for changes in that curve at a part of 100,000, right down there, right, is we have to make sure that we're not going to fool ourselves into measuring one of those things. Okay? So we look in 5 frequency bands. So it's like we're looking in 5 TV channels at the same time. Okay, we've got them all up there. We're looking at all the fuzz, right? We're kind of moving our antennas around. And so that's what we decided to have 5 frequency bands so we could make sure that we don't confuse ourselves with the galaxy. So here is Dave Wilkinson, who was actually, he was the guy who was the first one to really go after these measurements with the singular purpose of measuring these tiny temperature changes, of measuring, quote, the anisotropy, right? The not isotropic, that's what anisotropy means. And he had been doing this with Bruce Partridge, who recently retired from Haverford College, since they made the first instrument to do this and they used it near the football field at Princeton in 1967, and had been working and teaching most of the people in the field how to make these measurements since then. Certainly all of our colleagues and most of the people on our team, and was working with Chuck on the COBE satellite. So he, like many people, were thinking about these measurements. Here's the first version that he sketched out, and it has some of the elements that ended up in WMAP. But I think what really happened is when we got this whole team together, we met down at Goddard, it evolved quite a bit from this point, as you'll see in a minute. Dave, so had a huge influence on the field. Dave passed away in September of 2002, but in enough time that he saw the results of the satellite. He saw the data. He saw these maps that we'll show you in a minute, and could see what happened. And then when we actually came out and released the data, we renamed it in his honor. So this is the W in WMAP. Okay, so who's the team? Here is a slightly edited version of the original proposals, just edited in the sense that, of course, Dave Wilkinson passed away. John Mather, who was one of the original proposers, went off to work on the James Webb Space Telescope. A number of other people have joined us to work on the data from all over the place. Here's the crew. This crew right here in blue is still with the project, still working on it day to day. Many of these people are working on it day to day, but have moved out of the Princeton, Goddard, Hopkins sphere. And then here's the crew who have graduated and gone off and to do other things. But you can see it grew quite a bit, and it took all these people to get the science out of this that we have. So let me show you now what the satellite looks like. So after a lot of work, after that proposal, we came up with that design, and you saw it on the front. So here it is, satellite. I'll stop it at some convenient point here to highlight its features. There. Okay, so this is up there, and we'll talk about that a little bit more in a minute. But you can see, if you look at it, right, that this thing right here, that's a primary reflector, a secondary reflector. Those are called the feeds. So the radiation comes in from the sky, bounces off there, comes into there, bounces off there, and into there, right? This just looks like a TV satellite dish, right? Okay? So it's really, it really is. There's a lot in common. But so the thing is, right, we want to measure these temperature differences. We don't care about that. We care about that 2.725 Kelvin, but not for this measurement, right? That is a constant. We want to look for changes in that. So that's why we have two of them. So there's one looking one way and one looking the other way. And what we do is we always measure the temperature difference between the two of these, the radiation coming in from two sides. So it comes in here, this side bounces off that way, this side bounces off that way into these feeds, and I'll show you what the inside looks like in a minute of the satellite. So sort of the business end. So the radiation comes in like that, and now it turns out that your TV would be more sensitive, and I don't recommend this, if you cooled it down, right? You put your TV in the refrigerator or something like that. It would be more sensitive, but you wouldn't get, it wouldn't be so good for reception. So what we want to do here is cool down the amplifiers. And so just at the base of these feeds, the feeds funnel the radiation down into here, into amplifiers. And these are they're fancy, very fancy TV amplifiers. Okay? And they're cooled. And one of the things we were worried about in the satellite is, we're measuring these tiny, tiny temperature variations, right? We are measuring, when you combine things, millionths of a degree, right? So we wanted to cool it down and we wanted it to be very stable. So we didn't want any cryogenic coolers pumping away or anything like that. And so we, quote, passively cooled it. And that's what these guys, these big elephant ears, we'd sometimes call them, do. Those are just big radiators. And those are just sitting out there in space. You'll see where the sun is relative. The sun doesn't shine on this. And they're just radiating away and cooling down these amplifiers to about 100 degrees above absolute zero. And so we get great sensitivity, and so much more sensitive than your TV sets. And we know it's very stable. There are no variations. The variations are absolutely tiny. So let's now go inside. So these are the feeds again, right? And they're two sides, right? Because we want to measure these temperature differences. And you can see this, from your point of view, it's probably this rat's nest in here of components. But these are all various amplifiers and waveguides and things like that, right? Some components that you'd see inside a microwave or some transceiver, any radio telescope you went to would have things like this. So here are there are all these feeds here. There are 10 feeds on a side. That's because we look in five different frequencies and we partition them differently between the feeds. So here they are at about 90 degrees. Here are then cold microwave components. And then we amplify the signal a little bit, right? The differential signal from both these sides. And then a little more getting down here into the warm microwave components. And then we ship it out. So this is sort of the heart of the instrument. So that's a CAD picture, right? Computer-aided picture. Here's the real thing, which we built. This is sitting down, or was sitting down one time at NASA. Now it's over 1.5 million kilometers away, floating away from us. And this is, if you will, so these have, once you put them through the telescope, they have a resolution sky like this. So because of these are lower frequencies, so longer wavelength, so the mirror, the reflector, which is about 1.4 meters in size, can only focus this so much. And the smaller the wavelength you go, the tighter it can focus it. So you have very high resolution here. Down, and the radiation is about 3 millimeters long. And up here, where it's 1.3 centimeters long, you have worse resolution. But there it is. So we're always looking at the sky differentially with these sort of eyes, if you will. Okay. So now, moving back in. So this is just to give you guys, you tech-oriented guys, a sense for what goes on. So here again are these two feeds, both sides. And we came up with this design. Again, this emphasis is on the stability here. We actually take the radiation, we mix it, if you will. If you think of optics, we have the microwave analog of a beam splitter, a beam combiner. So that's what that thing called the magic T does. We then amplify it. We actually then phase switch the radiation. So not only do we look back, we compare the radiation from these two sides, but we actually switch it back and forth at 2,500 hertz. So very rapid switching, right? And then we uncombine it again and then come out and detect it. And what made this satellite, the key technical element here, were these amplifiers right here that were developed by Marian Pozbozalski at the National Radio Astronomy Observatory. And these enabled this experiment and many others. So here's the key thing for us. So why is it so stable? This is just the noise level here as a function of frequency. And what you're supposed to notice, don't worry about too much here, is just that unless you go to very, very long time scales here, that it's no matter sort of if you're looking at variations like this or looking at variations like this, it's all the same. It's just constant, right? It's just, the thing is a rock up there in space. Absolutely. We measure the temperature variations in components of the satellite in microkelvin, hundreds of microkelvin. But that's, you can imagine measuring the temperature outside, on your kitchen thermometer. We measure the temperature of this thing, and it's stable to way more accurately than you can measure with a home-based thermometer. Okay, so we built that. We built it at Princeton and Goddard, and then integrated it all down in Goddard, and the whole team that Chuck was telling you about, the rest of the team was building up the spacecraft and designing it, and we merged these together. And then here, it launched on June 30th, 2001. And I think when we were just talking about this the other day, right? When we started the project, it was something, this rocket had a 95% success rate. And we said, perfect, 95% success rate. That's great, no problem, we're going to go ahead and do this experiment. After working on it for 5 years, and the success rate, I guess, had improved a little bit, but still just saying it's 95%, and going down, we got down to the Cape to launch it. 5% failure rate was unacceptable. How could that possibly be, all this work, right? So anyway, of course it worked. We got it up there, and here's where we are. We're in this very special place, as in a minute. The moon is over here. We're about 5 times further away than the moon in this big loopy orbit out there. And you'll see how we look in a minute from that orbit. So there we are, and here's the way we observe. So the picture you want to get is you are looking out there roughly from the point of view of the sun's behind us. You're looking out. These are the solar cells right there, so that's where we get all of our power, right? The Earth is sort of back from your vantage. The sun is back there. The moon is back there. And then we're looking away. That's why we want to be out of L2, right? Because we're looking for microkelvin, right? And how hot's the sun? It is 6,000 degrees, right? We have to reject that to a huge level. So there we are, and this is how we spin. We're just spinning around. So those 2 antennas, just going around all the time. That's all it does. It spins around, measuring the temperature differences. That's what the red and the blue indicates there. And it just spins around, and it precesses as well. It's like a not an Etch-a-Sketch, but a spirograph pattern. And it just spins around like that, and it covers in an hour about 30% of the sky. And then this whole pattern there, so you can see that spirograph pattern. This whole pattern, so it spins around. You heard that rate a minute ago, about 2.5 kilohertz, 2,500 switches per second. It then spins at 2.2 revolutions per minute. It does this precession every hour, and then this whole thing moves around the sky, right? Because it's L2 spots, great, right? The sun and the Earth are always behind you, and the moon, and we're actually orbiting the sun. Okay? It's like we're our own little planet out there. Okay? We're just orbiting the sun, and then that sweeps it out. So in 6 months, we then map the whole sky. And we did this for 9 years. Right? We designed it for 2. It worked for 9. And so we have then combined those to get 18 maps of the sky. So here's what we get. So this is, so now let me orient you. So here, Chuck's going to throw me the universe here. Okay. So here is what we're looking, so here's the way to think about these maps. This is, if you had a globe, right? You would look at the globe and you would say, okay, there's Beijing, there's Hong Kong, there are the Philippines, right? You just look down and there they'd be somewhere down there near the equator. Okay. Instead, we're just looking out. So imagine yourself in the middle of this and we're looking up at the sky. Okay? And the first thing you see is what strikes you here, and you'll see there, is this red band. That's from the galaxy. That's emission from our galaxy. But you can see And if you look off the band, you see all these hot and cold spots called blue and red. Okay, and now you can see the 5 frequency bands, why we cared, right? As it cycles through these frequency bands, you see how the signal from the galaxy gets to be less and less and less, okay? Because that red stripe gets smaller and smaller and smaller. And then, but you can see the contrast, those blue and red spots in the northern and southern galactic hemisphere, as we call them, stay the same. Okay? So this is color-coded so that the cosmic signal has the same color contrast in each slide. And so, you know, David will tell you some of the fancy stuff we do, but more or less we just get rid of the galaxy, and we look up, and we look at the top, and we look at the bottom, the northern hemisphere and the southern hemisphere, and we look at those spots, and we analyze them. Okay, so and then this is the picture you want to keep in your head for how that all works. So we're just looking out. So it's all over the sky. Okay, so what do we do now? So let's just zoom in on a little bit of that picture. So in this, we're somewhere right down in here. Okay, so we're just going to carve out a little bit there. Okay, and this is a big, this is a big patch of the sky. So let me zoom in on that, right there. This then is 5 degrees across. And if you remember back to when I showed the beam pattern, right, that thing that showed our resolution on the sky, you might remember that our resolution is a small fraction of that. These splotches here, these red and these blue splotches, are not from the resolution of the instrument. They're completely resolved. Okay, so you can look at that, right? And someone tell me, what's sort of an average size of that splotch there? Roughly. Yeah, degree. It's right. It's roughly, it's of order a degree, right? So now, if you remember back to that plot that Chuck showed, right? I'll draw it on you. I don't have it here, but that spectrum went up like that and went down and had those little bumps there. Remember that? So that big peak right there, remember the angular scale on that peak? It was a degree. That tells you where most of the fluctuation power is. It's on a degree angular scale. And this is what we see. And so here's what we do. And this is sort of the core of our measurement. This is the sort of a watered down, this is a version that David would chide us for. But this is a simplified version of how to think about the sky. And so here it is. Here we are looking out, and we see all those hot and cold spots out there. And they're made from the mechanism Chuck talked about of the plasma flowing into these potential wells, these gravitational potential wells. And what we can do is we can just more or less just stack them up. So this is just taking 12,000 hotspots and stacking them up. And what we can do is we can now, since we have so many of them, and the measurements are precise enough, and we know there's no galactic signal in there, right? We know there's no contamination. We say, okay, this is it. This is sort of a spot size. And we can measure how big that is. And you're going to say, well, why isn't that 1 degree? You just told me they're about 1 degree, and don't worry about that. Okay, so that's just because of the different conventions here. But the point here is that we can measure the angular size to that spot to percent level accuracy, right? Because we have so many of them. Okay, so we have the angular size there, measured very well. And now what David and colleagues were doing before we got all involved with this was computing how wide across that is in meters. Okay? So there we go. So because you can do this because the physics of this stuff is so simple. The universe was much, much simpler back then when this radiation was made, right? We could describe it with a handful of parameters. And so this is not difficult physics, right? So we can compute in meters how big that is. We can measure in angular size how big that is, right? So just going back to high school or whatever, before high school, right? If you know that angle and you know that size, what do you know? You know you got that distance there, right? And you know that distance. So this radiation is coming to us effectively from the edge of the observable universe. This comes across the whole universe, is the diagram that Chuck showed. So we have this huge triangle from us out. We know in meters how much it is, because we know the meters across, we know the angular size. So that gives us the overall size of the part of the universe that we have access to. So we have a standard yardstick out there, if we do. So we get the distance, as I just said. We know the distance. We know the speed of light really, really well, right? Measured to exquisite accuracy. And from that, we can go and deduce the age of the universe, right? Because we have the size, we know the speed of light, and there it is. And when we actually do it, it's somewhat more involved than this, but that's how, more or less, that's how we deduce the age of the universe. So that's one of the things we can tell. And as David will tell you now, we can do much more than that.